Section 3.11 is about hyperbolic trig functions. The main thing you need to know is that the hyperbolic sine function is defined in this manner, and the hyperbolic cosine function, cosh, is defined in this manner. Sometimes this is called sinh x, and this is called cosh x. The only difference in the two definitions is basically this sign. The other four hyperbolic trig functions follow pretty naturally. They're exactly what you'd expect them to be. First example, we're going to prove the identity that the cosh squared minus sinh squared is equal to 1. The way that we're going to do everything when it comes to hyperbolic trig is we're just going to go back to the definition. So I'm going to start with the left-hand side. And I know that cosh is just e to the x plus e to the opposite x over 2. And I know that sinh is almost exactly the same. So the first thing I'm going to do is square this guy. And here I have e to the x times e to the x gives me e to the 2x. And then I'm going to have, when I FOIL things out, my two middle terms, I'm going to have e to the x, e to the opposite x. And when I multiply e to the negative x times e to the negative x, I get plus e to the negative 2x. And in the denominator, I'm going to have 4. So let's move over to squaring this function. Get e to the 2x minus 2e to the x, e to the opposite x, plus e to the opposite 2x. Okay. So you can already see that when I combine these, that these two will cancel, and so will these. But the middle terms won't. I'm going to get 2 plus 2, 4 copies of e to the x times e to the opposite x over 4. And we know that this is just going to be equal to e to the 0, which is just 1. Okay. So we have actually proved the identity. So here's just another similar to the previous example. We want to show that this function is odd. And remember, a function is odd if I input the opposite of x, I get the opposite of f of x. So let's do this for the sinh function. I'm going to write it in function notation. And let's see what happens. So again, I'm just going back to that basic definition. Okay, the basic definition was that sinh is e to the x minus e to the opposite x over 2. So in this case, I'm going to have e to the opposite of x minus e to the opposite of x over 2. And this gives me just e to the opposite x minus e to the x over 2, which is the same as negative e to the x minus e to the opposite of x over 2. And this you can see is just the opposite of sinh x. So this is odd. Okay, so here I've just reversed the ordering there. Here's a limit question. Once again, same idea. We're just going to go back and use the definition of hyperbolic secant. And remember, hyperbolic secant is defined naturally as 1 over hyperbolic cosine of x. So that's going to be the reciprocal of hyperbolic cosine. Okay, so we're going to want to compute the limit of this function. A couple of things I'm going to point out when you're computing limits of hyperbolic trig functions is to remember that they really come from these two basic functions. So the limit as x approaches infinity of e to the x Well, let's look at this function. It looks something like this. It's just infinity. And similarly, the limit as x approaches negative infinity of e to the x is just 0, right? Because we can see what's happening over here. I'm also going to take another look at this function. So the limit as x approaches infinity of e to the opposite of x. Well, let's just take a quick look at the graph. We know that this is just a reflection of this function over the y-axis. So as x approaches infinity, this limit is 0, and the limit as x approaches negative infinity of e to the opposite of x. Well, if we look at this, we see it blows up. So this is infinity. These limits are useful to look at when you're computing limits of hyperbolic trig. So now let's go back to the original question. The limit as x approaches infinity of hyperbolic secant is equal to the limit as x approaches infinity of 2 over e to the x plus e to the opposite of x. Okay, so we know that the numerator isn't going anywhere, but we know that this is going to blow up to infinity, right, because of this limit. And we know that as x approaches infinity, e to the opposite of x goes to 0. So this numerator is going towards 2. The denominator is headed towards, infinity plus 0, so the limit here is 0. Similarly, if I take the limit as x approaches negative infinity, something very similar will happen. If I approach negative infinity, let me just write this down. This expression. Well, then we know that this is going to 0, right? And e to the opposite x, as we approach negative infinity, this is actually now going to infinity. So once again, we get 0. The last thing I want to talk about is derivatives of hyperbolic trig functions. Once again, if we want the derivative, we're just going to use the definition. We're going to take the derivative of e to the x plus e to the opposite x over 2. So this is just 1/2 d dx of e to the x plus 1/2 d dx e to the opposite of x. And this just gives us 1/2 e to the x minus 1/2 e to the opposite x. So this is just 1/2. Or let me write this. And this looks exactly like the hyperbolic sine function. Okay, so what we find here is that the derivative of hyperbolic cosine is just hyperbolic sine. Notice that this is different from unit circle trig because there's no minus sign. So that's one thing you have to remember. Here's a summary of the derivatives of the 6 hyperbolic trig functions, and you can use, similar, you can figure out these derivatives the same way you figure them out for a regular trig. Now, the one thing I want to say is that they're almost exactly the same as the unit circle trig derivatives. The only difference you're going to see is in the sign of these 2 derivatives. So be careful with those. This one and this one are slightly different just by this difference in sign. This one's missing the minus sign. This one has a minus sign. The last thing I'm going to do is just some quick differentiation examples. So here's my function. It has a hyperbolic trig function in there. So y prime, in this case, using the quotient rule, I'm going to take the derivative of the hyperbolic tangent times e to the x minus the derivative of the bottom function times the hyperbolic tangent, and everything gets divided by the bottom function squared. So this will give me hyperbolic secant squared times e to the x. Okay, now you can simplify a little. You can pull out a factor of e to the x from the numerator and denominator. And you're left with this function. So that's y prime. In this example, we have a lot of the chain rule going on. So y prime here is 3 times hyperbolic sine. Now I have to multiply it by the derivative of the inside function. And I have to apply the chain rule one more time, multiply by the derivative of the inside function. So you can clean this up a little bit, but, oh, sorry, there should be a squared here. So this 3 times 7 gives me 21, sinh 7x plus 1 times cosh 7x plus 1, and this was squared, remember? And that's our derivative.